So welcome everyone. It is my pleasure to welcome you to this new appointment of our 40U40 lecture series on combustion. It is my pleasure to welcome today with us Professor Claudia Lopez Camara. She earned her bachelor in chemical engineering and master's in nanomaterials and nanoscience from the University Rovira Virginia, Spain. She completed her PhD in numerical combustion and at the University of California, Irvine in 2020 under the supervision of Professor Rankin and also collaborating with Professor William Sirignano. She has a number of collaborations already since the PhD with the University with CAUT and with Lawrence Livermore National Labs as well. In the postdoc, she continued at the University of Duisburg-Essen in Germany with Professor Wiggers and Professor Schulz. And since 2024, she's assistant professor. So recently, she was appointed professor in Eindhoven University of Technology, where she actually researches nanomaterial synthesis for energy and sensor application. She's also very active in diversity in STEM and so broadcast science to general audiences whenever it's possible. I thank you again, Claudia, for having accepted our invitation. So today you will talk about gas phase synthesis. You will give an overview and study cases for fuel-layer graphene and coated nanomaterial. I leave you the floor and thank you again.
Perfect. Thank you again. And thank you for inviting me and for all of you to be here with us today. So as Alessandro has mentioned, I am recently appointed professor at the Eindhoven University of Technology. Therefore, most of the things that I will be talking about today, it's work that I've been doing during my postdoc part. But nevertheless, during my professorship, I will continue investigating this line of research, which is gas phase synthesis. So without further ado, we will start. So I would like to start first, providing you some fundamentals about what is gas phase synthesis. So gas phase synthesis, we need a reactor. In this case, we have a closed reactor, so we can collect as much nanoparticles or nanomaterials that we are producing. And then we have the precursor coming from the bottom of the reactor, as you can see here. Every time I say precursor or reactant, is the same thing for me. So we have the precursor that is entering the reactor, and then we have filter that will be collecting all the nanomaterials that we produce. So when the precursor enters to the reactor, the first thing that it finds is a high temperature region, either being a flame or a plasma, or even a hot wall reactor. It would be a wall. So basically, it's a high temperature region. In this case, I put a flame there. And when that happens, the precursor evaporates and decomposes, and then it further nucleates, and then the particle growth happens, and the particles get deposited on the filter. So this is the fundamentals of all sorts of gas phase synthesis. And the good thing about it, or the advantages about gas phase synthesis, is that it's scalable, cost-effective, and you have powder as a result. So that's different than when you use wet phase synthesis, because in those cases you get a solution, but that's not the case here. We get powder. Unfortunately, as any process, you also have some drawbacks and some things that you have to take into consideration and try to minimize or mitigate. And those are the following. So as I mentioned, it requires high temperatures. So that's something we have to take into account. It also has some challenges on the stability, and it yields agglomerated nanoparticles and particles. Therefore, we have to take clever approaches to face that. So then we will see the first kind of gas phase synthesis, which is a flame reactor. A flame reactor is specifically the one that I'm showing here, which is a setup that is in University of Duisburg-Essen. It accommodates a spray sim burner. And the spray sim burner working, it's as you see in this picture over here. And it has this blue halo from a methane oxygen flame, which is used as a pilot in order to ignite the flame that it's produced by the precursor. In this case, the precursor that is being injected is ethanol, and that's why the flame is of this color. But if we inject other precursor, for example, this, we would get a much more virulent flame and also another color of flame. And it will, of course, depend on the chemicals that are in the precursor that we inject, that we have other colors. So with that, we can also create an array of different battery and energy-related materials. I put here two major schemes of the batteries that are known, like the liquid ion battery and the solid-state battery. So as examples of materials that we can produce with a spray-syn burner, a flame reactor, are these. Those are just examples. So for example, for the liquid ion batteries, we can produce electrode materials such as all of these that are like here, like high entropy oxides, perovskites, and so on. And for solid state batteries, we can perhaps also produce electrolytes. And some examples about it are LLZO, LATP, and so on. So those are just some examples, but of course there are many more materials that you can produce using a spray-syn burner and for other purposes, not only for energy applications. Then the spray-syn burner and flame reactors are not only accommodating this kind of burner, but can also accommodate other kinds of burner. And this is another flame reactor. The principle is the same. You see the casing of the reactor and then the filter in the right side. And I'm not sure if I can put a pointer, but I believe I could at some point. Well, this is the filter, as you can see. So just making you sure that, that we understand what we are talking about. And yes, basically what we have here, it's not a spray-syn burner, but a matrix burner. And a matrix burner looks like this. And the advantage in comparison to the spray-syn burner is that the spray-syn burner always runs in premixed flames, which means that the fuel and the oxidizer are premixed or mixed before they are ignited. Here, the matrix burner allows for premixed and non-premixed flames, and then you have and also diffusion flames. So you have the precursor and the fuel coming from the big holes of it, and the small holes are the oxidizer, oxygen, it's coming out from it. So when it's lighted up, it looks like this. And this design has been purposefully thought in order that it's easier to also do simulations about it. So that's why it was, let's say, developed. With this kind of strategy, we can create core shell nanoparticles, for example. And the core shell nanoparticles look like this. So the stripes part of this nanoparticle that you see in the TM picture that it's on your left, it's the core. In this case, is titanium dioxide, and the surrounding area of this stripe part, which is amorphous material, it's silica. Therefore, this nanomaterial, it's a core shell nanoparticle with the core of titanium oxide and the output of silica. But with the same approach, we can also do iron oxides covered in silica, creating the iron oxides or the titanium in the previous case by the flame, and then covering them with jets that we will see in a moment. Then we also have hot wall reactors as a, let me see if I can erase this thing 1 second. Good, perfect. So yeah, we also have hot wall reactors, which are also another way of gas phase synthesis. And in the hot wall reactor, basically you have, you can imagine that you have a cylinder, and in the output you have a resistance that it's hitting that cylinder, that's a ceramic cylinder. And inside you have a nozzle that it's what it's shown here in the left. And it's from the nozzle you get your precursor into your hot wall reactor, and then it nucleates and it grows, as I mentioned in the very first slide. So in this case, as an example, we can, for example, put silane as a precursor or reactant, and then we can put ethylene as our fuel. And then afterwards, we can get amorphous silicon nanoparticles or amorphous silicon carbon nanoparticles, in this case also for energy applications, but we can do other reactions as well. To give you an understanding on the dimensions, how this hot wall reactor looks like, this is a picture of one of the hot reactors that are in Duisburg-Essen as well. So it's actually a little bit hard to see, but if I can pinpoint it to you, you can see that there is here, this over here would be the hot wall reactor, and this, which goes also down to another floor, it's the filter in this case. So you can see that it's quite bigger, quite much bigger than the previous reactors, and that explains that you can get a kilogram per hour in terms of nanoparticles produced. But nevertheless, all the gas phase syntheses are producing, they all depend on the filter size. So the bigger the filter, the longer you can run the reactor, pretty much. Good. So then we will move on. Let me see if I can deal with this again of cleaning the colors. Sorry. Annotate. Okay, perfect. And yes, so we also have the plasma synthesis, which is another kind of gas phase synthesis. And in this case, we use a microwave plasma. That's what it's pictured in the image. And this microwave plasma is the high temperature region in this case, where we decompose or evaporate, well, in this case, decompose the evaporated already, the gas phase that we put inside the reactant that is already in gas phase. And there is also possibilities of adding a hot wall afterwards or another module of inline processing of the material. And doing these plasma reactions, we can, for example, obtain graphene. So this is a sample of graphene that we created using the microwave plasma reactor. And is this very crumbled material. So the material that you see very plain and very structured, that's actually part of the TM holder for the sample, and the sheet, let's say, of very crumbled material, that's actually the graphene that we get from the plasma reactor. So as well as you can do hybrids of plasma reactors with hot wall reactors, you can also do flame reactors, which is the same reactor that I showed you before with the matrix burner, but with plasma in line. And this is not a microwave plasma, but it's a dielectric barrier discharge plasma. And that is because in this particular case, we tried to avoid the agglomeration of nanoparticles by charging them right after they were produced by the flame. So this is something that, as a researcher, we also try to get creative to find ways to avoid this agglomeration and those non-desirable results that we could be getting if we don't use one of these approaches. So look, after this outlook or overlook of all the techniques, we will look into the graphene and soot evolution. And you might think why we want to look into that, because graphene and soot is very well known. However, when we were thinking about it, when we use gas phase synthesis to create them, we did not know yet the response of this question, which is the role of the precursor and how that affects the produced material. When we were thinking about it, we also had another question that we wanted to answer, which was, how does soot and few layer graphene evolve as they move further from the high temperature region? So we wanted to know, basically, first of all, what is the precursor, what that will create? And second of all, once the material is created, how does it look like until the time that we can actually collect it in the filter? Because in the time in between the time of creation of the material to the time that we can collect it in the filter, there was not really anything known in terms of actually getting sampled rather than doing, for example, laser diagnostics. Therefore, the way of doing it, we thought, well, what is the best gas phase approach to do it? And we thought that perhaps plasma would be the best, because plasma synthesis for creating few layer graphene. It's a technique that does not require substrate or catalyst. It's not new, and it also enables ultra pure process, which makes the questions to be answered, let's say, in an easier or facilitate to be answered rather than having other things, external things that might change the answers or that might change the process. Then it's also it's established for different plasmas to create graphene. Therefore, we thought, why not? Let's do a microwave plasma synthesis. And this is basically a drawing or a schematic with pictures from TM and AFM, sorry, about the evolution that some previous people had reported on literature. And basically the plasma region is the one that I highlighted here. So with that, we were going to be using the microwave plasma, and the microwave plasma setup that we would use was one that basically we were injecting the gas inlet, the reactor gas inlet from the bottom. So that's where the precursor was being injected. Then we had the plasma resonator, the microwave plasma resonator, which is the orange part there. Then we had the filter as the beginning. And then the very particular and special part of this setup was the top part, which is a thermophoretic sampling device. And that is basically a piston, a pneumatic piston, that introduces a TM grid, so an electron microscope grid, in order to collect sample from different heights, that depending on the on how much pressure we put in the piston to go in. So basically, also the it pushes the piston in, shielding the TM mesh, and it brings the piston out, also shielding the mesh. So you only collect nanoparticles from the height that you want. And that's how it looks, the column of hot gases that came from the plasma resonator. And then this is the different heights at which we wanted to collect nanoparticles, or in this case, nanomaterials, because we had graphene and soot. So we had 4 different heights from 12.4 to 24.4, having as a reference the nozzle of the plasma, which the nozzle of the injection of the gas inlet in the plasma, which was at 0, let's say. And I will show you now a very slow motion video of the insertion of the probe, so you can see what I was referring to. So it shoots it in, it shows the mesh, it brings it out, and then we take off the whole piston and we collect the nanomaterial. So that was how we did it. And we have 3 case scenarios, and the 3 case scenarios, because we wanted to understand which was the role of the reactant or the precursor, we used, for case 1, we used ethanol, and for case 2 and 3, we used toluene. And the difference between cases, apart from the reactant, was the flow rate, which at the end of the day means that the carbon content was different. And based on previous results from our lab, and also in previous results from others, we knew that the expected materials based on the carbon content and on the reactant was going to be graphene, soot, or a mixture of both. But we needed still to check if that was right. And we did check it. And we saw that indeed our expectations were achieved. And for case 1, we saw these flakes. So basically what you are looking at in picture of case 1 is the TM mesh, so lazy carbon. So if you see this very nicely structured carbon, that's not our sample. That's just the support where our sample was being fixed by thermophoretics. So basically by the difference in temperature, our sample was being deposited there. And our sample, what it is actually, it's the flakes that are on the top of it. In case 2, you see the soot, which was collected, which was the expectation as well. And in case 3, you can see in the left side, this crumbled graphene sheet attached to, to the support of graphene. And in the right side, you can see this also soot that we've obtained. So we obtained a mixture of both. So we wanted to understand a bit more about it and a bit more about the evolution, how it achieves how does the graphene and the soot look like from the beginning to the end where we collect it in the filter. So looking into the graphene, which is case 1, the way that we did some histograms for accounting for the size of the graphene, and the way that we described the size of the graphene was by the ferrodiameter, which we identified as when we had a very crumbled graphene. Usually we draw an ovalene, as you see in the picture on the top right. We draw an ovalene surrounding the full flake, and we get the largest diameter of the ovalene as our ferrodiameter. And that's what we took as a reference dimension and as a reference measurement. And then if you look into these numbers and into these plots in the big lines, we can see that when the measurement, when the sample has been taken at 12.4 centimeters above the nozzle, so that would be the plot, the first plot in your left top. It has an average of 321.3 nanometers of length, while if you go towards higher heights above the nozzle, like 24.4 centimeters, the plot that is on the right bottom, the size change, it actually decreases to 196.9 nanometers, about that. And that tells us, and this together with the TM pictures and the VET data, tells us that basically the graphene, as it moves farther away from the nozzle, it gets more crumbled and it gets more self-folded. So the area actually increases, even though in a 2D picture, you would see a much more smaller, let's say, graphene flake. For soot, it actually happened the opposite. When you are, for example, in the lowest high above nozzle, so 12.4, which is the top left plot, you have about 16.6 nanometers. However, as you move farther from the nozzle, let's say the filter, for example, which is the last plot in the bottom, you see that the size is already 24 nanometers, and that's in diameter, because soot particles, the approach that we use is that they resemble spheres, so we basically count the diameters. And what it tells us is that the diameter in general increases as we move farther from the nozzle, which tells us that there is still surface growth when the particles are being moved away from the nozzle. For the third case, however, we saw that once in the 12.4 centimeters, which is the lowest sampling point, we got graphene and soot, as we saw. However, when we go to a higher heights above the nozzle, so farther away from the nozzle, we only could see soot in the TM, in the electron microscope. And that could have been happening for two reasons. The first one is because the few layer graphene crumbles so much that it becomes very small, and they look like spherical particles, but they might not be spherical particles, or they might not be soot, but they might be graphene, but it's kind of really extremely hard to see the difference. And the other option is that there are so many more soot nanoparticles than few layer graphene that when we check on different regions of the sample under the electron microscope, we were not lucky and we didn't find graphene. So these could be two things that are happening at the same time. And therefore, we did achieve our answers. So to which role is of the precursor and how that affects to the produced material, we confirmed that the reactant and its concentration determine whether few layer graphene, soot, or both are generated. And even though I did not show it here, we also have numerical simulations that explained that C2H2 in the post-plasma region is the main factor to determine the ratio between the soot and few layer graphene. Moreover, to the question of how does soot and few layer graphene evolve as they move further from the high temperature region, we saw that the initial carbonucleation is placed below 12.4 centimeters above the nozzle, because at the lowest point of sampling, we already see graphene fully formed and or formed and soot form. Therefore, it should happen even in a lower position. And for graphene, we saw that we did have flat graphene at the lowest sampling position, and it's crumbling as we increase from the high above nozzle. For the soot formation, though, the soot particles show surface growth. That's what explains that you have much more, the diameter, the medium diameter is larger, but even though the VT area it's lower. And coalescence at the first high above nozzle samples, and its increased aggregation level with increased high above nozzle as well, which I did not show that, but we saw that too. So with that, after so many hours being spent in the TM, I was starting to see some patterns, actually. That was an unexpected observation. And I thought, well, this might explain a story, because these patterns are repeated and repeated. And I saw so many pictures, and I saw so many samples that we did for that work. And therefore, I pitched in this hypothesis to my colleagues, and we actually checked it out as well. So I pitched in a hypothesis for few layer graphene formation, and that consists on the next. So the step one would be the formation of the growing rounded sheet of graphene, single layer. Then the small rounded sheet was formed in step 2. And in step 3, this small rounded sheet was formed and was also growing. And eventually this growth, as you can see in this video, as well as in the picture, because the graphene was growing so much and it was just one layer of graphene, it was just mechanically unstable and was, self-folding or crumpling in a random way. Not nicely, let's say. But in some cases, instead of crumpling in a random way, we were seeing that this rounded graphene folding was folding actually nicely. It was self-folding nicely, as if it was like, for example, an envelope, if you want to think it at this way, as you can see it in this picture. And in these cases that the graphene was folding, let's say, nicely, it could happen 2 things. One was that you would get curled, like a graphene that was curling into itself, like as you can see in the video that I will play as a moment more. Let me see 1 second, because yes, there it is. So you can see in this video that it's tilting the sample, so you can see that it's the sample from different angles and it's rolled, as well as in the picture in the middle. So it's a rolled graphene, let's say it's a curled graphene, better said. And then in the last third picture, we also see quadrilateral graphene sheets. So if you start folding as if it was in a bed sheet even, or a paper, you finish ending up with these quadrilateral graphene shapes. And we observed that. However, as I mentioned, perhaps at some point earlier, when we get into the filter, the graphene is already very crumbled. And therefore, that means that either way, it leads to a randomly crumbled and folded graphene sheets. And going into more detail into these observations, we also wanted to know, first of all, is it true that it's just a single layer graphene that it's rounded? And we were lucky, actually, because TM sometimes is a matter of luck. And we found this flake. Picture A and picture B are the same thing, but picture B, I put some color on it. So you can see that the graphene sheet, for the people that haven't spent so many hours in TM, it might be easier to compare both pictures. So if you see in picture B, the graphene sheet, the rounded graphene sheet, it's marked by a green line. And the part where the graphene sheet is self-folded, it's marked with a straight orange line. And then the square, the blue square that you see in picture B, is actually, the zoom in is picture C of that square. And we did FFT of that picture, a Fourier transform, and that's what you see in picture D. And in picture D, you can see that there are 12 peaks, so 12 points, that is typically 2 two graphene sheets, because one graphene sheet would give 6 points, and here you see 12. So indeed, we confirmed that there was a single grounded graphene sheet layer formed at the beginning, and this was a proof of it. And in the self-folding, we see that there are two graphene layers, so that shows it. The other question we had was, well, when the graphene self-folds, does it break bonds or forms new bonds that other species or other components can attach to, or does it just bend, let's say, and form a curvature? And we confirmed that it was forming a curvature or bending by this picture, for example. So this is a very crumbled graphene, and you can see a zoom in of that part. And in the zoom in, you can clearly see in the pointed arrow that it does a curvature rather than a break. Therefore, it does not leave, let's say, bonds open, but it just self-folds, creating a curvature, which means that at that part, there is no possibility of growth anymore, because there is a curvature, there is no new bonds created. And that's something that we also wanted to see in this picture. So the top part, the A, B, and C, are just a piece of sheet that I got, that I cut it in a circle, and I made it in half, and then I did another folding in order to try to mimic the picture that I saw in the TM, that is the picture that you see below. So the picture that you see below, both of them are the same picture. The one in the left is raw picture, let's say, from the TM. The one in the right is the picture that I try to help people to see what it looks like, actually. So the green part is the part that would be mimicking the picture in C, that allows still to grow because there is no bend there, there is no curvature. However, the part that is orange, it's the part that you cannot have more growth of graphene. And that also explains perhaps why we get such a crumbled graphene. The also good outcome of that picture was that we got that this folding was 420 Armstrongs in length, and that was aligned with what we found in literature, in actually in numerical literature. So it was not shown experimentally yet, that it becomes unstable at some point, and then when you get 4 folds, because as if you count from this folding of the sheet, you are having 4 layers of graphene. That layer should be 420. That's when it gets unstable. So just to give you a better view of this, I also put together a video about this picture that I got in the TM, and you can see it here. So it's tilting the sample, so you can see a better idea of that sample being self-folded in this way. So with that said, we moved to another topic, or another topic, but it's still using the templating and the plasma reactions, the plasma gas phase synthesis. And that was kind of also unexpected. So we started first with the plasma reactor, so pretty similar to before, with a reactant coming from the bottom. We wanted to create composite materials for fuel layer graphene, so we were putting ethanol, so hydrocarbon reactant, the microwave plasma reactor, and then we were putting from the side silane as a secondary precursor in order to get some sort of mixture between fuel layer graphene and silicon, and we were passing it through this high temperature hot wall at 890 Celsius degrees, and then we were collecting it in the filter, and it was looking like this. So the idea was producing composite materials to see if it was possible and covering them in amorphous phase. So at the end of the day, in the filter, we were seeing this kind of graphene, so this kind of very crumbled sheet, and then these small particles around, which were silica. However, we were, okay, let's see what happens when we anneal it. So basically what happens when we put it in the oven for overnight. And that was actually a non-expected observation because my colleague put it at night and it was black, and I took it in the morning and it was white. And evidently something happened. Therefore, we were shocked and we wanted to investigate it. So as you can see here, there is 4 samples, but actually the 2 in the left are the same sample, 1 non-heat treated and 1 heat treated, and the 2 in the right, same thing. The only difference between the samples, apart from the heat treatment, is that one we used less and more silica. So we have more silane and therefore more silica at the end, and the other one we use less. So we looked into what was actually this powder, and we found out that we were creating a new template method. So using few layer graphene, which is the first column of pictures, so picture A and picture D, we have that there is graphene, but after we heat it up in picture D, we see that there is only silica left, and the graphene that was inside the silica, so we basically covered all the graphene in silica, and the graphene that was inside the silica, after we heat it up, it got burned, basically. We took it off. Therefore, what happens is that the silica kept the inside of the silica, it kept it as the shape of the graphene. So we created hollow nanoparticles of silica with the inside of a shape of a graphene. And perhaps it's easier to see it in the other 2 examples. The other 2 examples, instead of graphene, we use soot, because we wanted to see, well, if we can do it with graphene, can we change the shape of the, let's say, initial carbon material and cover it again with silicon and then burn the inside in the oven, or getting rid of it in the oven, the inside, and creating shell structures. And we could actually. So in picture, so the top part pictures are zoom out, the bottom part pictures are zoom in. So if you see picture D, picture E and F, it's actually the same thing. We departed from soot, same soot, exactly the same soot, but we changed the mass rate, the quantity, let's say, of silane. So obviously that translates on the quantity of silicon or silica, sorry, that we get at the end. And therefore we can create thinner or thicker shells or thinner or thicker walls to hollow nanoparticles. And we also checked further on if they were mesoporous or other sort of, or if they had porosity at all, and they were mesoporous actually. And something that I found to clarify, yes, we saw that the nucleation regimes of resultant porous nanomaterial are determined by the carbonaceous nanomaterial, which was basically telling us, okay, if you get graphene or you get soot, you can create different shapes. And the silane precursor, because if you use more silane, you get thicker walls. But something that it was really nice to see as well is that, okay, farther than a new templating method, is this useful? And we saw that using the soot as a baseline and coating them, and then of course getting rid of the soot in the oven, we got a removal of carbazepine, that is a drug that it's sometimes in wastewater for pharmaceutical wastewaters from a pharmaceutical industry. We get that in some cases, for example, in the kind of material that we have in the left, we got an outperform. So our material outperformed the commercial material that it's used for that purpose. Well, of course, other materials that we did were not as good, but some materials were better. So that's something that can be explored in the future as well. So going into the coated materials, because now we saw some sort of coating, but now we will be looking into coating nanomaterials using a flame reactor. So in this case, we wanted to do titanium dioxide and study how it's the best way to coat titanium dioxide, which is the best coating that we can create, or which is the best precursor that we can use for creating a silica coating. And for that, we created, we put together a flame reactor. So here you see a quartz tube, and in the bottom it's a flame, it's a burner, sorry. and we inject dispersion gas, which is oxygen and methane, and a precursor or reactant for titanium, so for creating the core nanoparticle of titanium dioxide, which is TTIP solution. We have sheet gas, we have a pilot gas, because if you remember, I mentioned that you have a pilot methane oxygen gas in order to ignite your precursor. And as soon as we put that in, we see a premixed pilot flame, because we are using, in this case, a spray-syn burner. And then we have core titanium dioxide nanoparticles. So because we want to do coating, we then have a coating gases. So we have basically jets surrounding the coarse glass that are basically inputting the coating precursor, different coating precursors that we tried for silica. And then you have the titanium silica nanoparticles afterwards. And the idea was also to try to avoid agglomeration of these coarse shell nanoparticles, and that's why we included a plasma, which was the DVD plasma that I showed you at the beginning. And then you have the hopefully not as agglomerated nanoparticles at the end. So with that, we thought, well, we depart from titanium dioxide nanoparticles as a reference with the plasma included, but without shell, because we want to study the shell. So those nanoparticles are about 8 nanometers. And based on that, we decided to choose TIOS, HMDSO, and OMCTS as 3 different coating precursors, because each of them have a different silicon to titanium ratio. So 1:1, 2:1, and 4:1, respectively. And therefore, the theoretical shell thickness was supposed to also differ and be higher as you move towards OMCTS, as higher ratios. So we were looking into this, and we saw that the first thing that we want to know is if the titanium dioxide are nicely homogeneously coated. And we saw that in all of the cases, in the 3 cases, in TIOS, HMDSO, and OMCTS, we do get this homogeneously coated. And you can see that from the pictures that this titanium dioxide, that it's this crystalline nanoparticle that has all these, let's say, zebra pattern, let's say. It's not really appropriate, but just to understand each other. So this nanoparticle, it's surrounded by this other coated material that is amorphous. So, okay, the nanoparticle, it is coated homogeneously, but is it coated with silica? And we did an FTIR, and we did see that the material that was the amorphous material surrounding these nanoparticles was indeed silica. So that was good news. Other thing that can happen when you have a flame is that you have hydrocarbons incorporated in your material, because, I mean, we do have hydrocarbons in the flame. And because of that, we checked on the content of carbon, elemental carbon, and we see that the content of carbon in all our samples was below 1.2%, which is basically negligible, which was good news. So there was no hydrocarbon incorporations in any of the samples, which was really good. And then after getting the BET analysis on the surface area of these samples, we saw some number that we did not know how to explain. Therefore, we looked into the TM a bit more. And for the HMDSO case, we saw that we had homogeneous nucleation of the silica from the precursor. So that means that we were creating nanoparticles that were not having titanium oxide inside, that they were just silica nanoparticles. And that's something that you want to avoid. And for the case of OMCTS, we saw that there was this thick structure, as you can see in this picture, this thick amorphous structure of silica coating and covering multiple titanium dioxide cores, which is, of course, not something that is desired. Therefore, we concluded that the most desired precursor for silica, for creating the silica shells is TIOS, as it performs best in terms of avoiding homogeneous nucleation and still providing a uniform coating of the titanium dioxide cores. So with that knowledge, we were okay, well, what about the plasma? Does it help or not? And we saw, based on this analysis, that there was a higher number of smaller aggregates when plasma was present, which means that there is a smoother slope. That's clearly seen in the case of TEOs or TEOs. And that means that there is avoidance of aggregation by repulsive column interactions, which basically translates to the fact of, okay, plasma works. However, there is a significant broadening on the distribution, which suggests that the plasma does not act in the entire reactant volume, which means basically that the charged species from the plasma are trapped in the mantle flow, so basically are just affecting the outer part of the flow, and do not reach the core of the flow of the reactor, which means that all of the nanoparticles are not seeing the plasma, and therefore the effect of the plasma is not as much as it could be. But in any case, coated particle agglomeration is found to be reduced to a certain extent. It could be even perhaps reduced more with other approaches, but it was already reduced a bit, resulting in a broader size distribution. So we know that TEOS works, we know that plasma works, so let's investigate a little bit more about the nuclei. Let's change the core to something a little bit more challenging or a little bit more interesting, and let's see what happens. And still, since we decided that TEOS was the best, let's keep TEOS. So let's change the core for iron oxides. In particularly, we are interested on magnetite and maghemite. Why? Because magnetite and maghemite in a nano size, they are super paramagnetic. And this is a very attractive feature. But apart from that, not only that, but magnetite, and iron oxides in general have been used for catalysis, medicine, cosmetics, clothing, agriculture. So they have been extensively already exploited, but there is still some possibilities. So because of that, they have been typically synthesized by chemical methods because they are allowing to control size, shape, and composition. However, it's still a floor to explore with gas phase synthesis. Therefore, that's where we were looking for. The questions that we wanted to answer in this case was, first of all, how does the quenching gas from the nozzle affect the produced material? So the idea is, if we produce a material in the flame, because we are going to do it in a flame as in the previous case, can we quench these materials fast enough that we change the material or that we stop the reaction somehow, for example? The second question, how does coating gas from the nozzle affect the produced material? So the question is, after the material is produced, can we coat it such as that oxygen cannot penetrate or cannot further oxidize the nuclei or the core of this nanoparticle? So that was other question. And then, can different phases be conserved, and how are their magnetic properties affected? So basically, in the same lines, can we avoid further oxidation and keep magnetite and maghemite, and how the ratio magnetite maghemite changes if there is any, or if we produce perhaps more of the other phases of iron. So we wanted to understand a bit more about it, and for that we slightly modified for the previous setup, and in this case we have a matrix burner, and we have therefore the fuel and the oxidizer being fed by different holes. Therefore, they are non-premix flames. The pilot flame is non-premix pilot flame, and that looks like this. And when we inject our precursor, which in our case is argon with iron pentacarbonyl in gas phase, then the flame looks like this. And once we start creating material, in this case iron oxides, they will be flying up. Because basically we are directing those hot gases through the quartz tube, and then we have a quench gas. So basically we have nitrogen that is being injected in order to see what happens to the nanoparticles, and then we also have coating gases, which we decided to keep TEOS because it was the one that we saw that it worked better in the previous study. And then we get core shell nanoparticles, and we decided to stop there instead of putting a plasma reactor as we had, or a plasma device as we had in the previous one, because that was already complicated enough. So with this, we looked into three different cases, but three different configuration options. So if you look into the right side, you have three options, option 1, 2, and 3. And in option 1, we have the quench and coating nozzles together, but at 278 millimeters from the flame. While the option 2 is the same thing, but closer from the flame. And option 3, they are separated by 66 millimeters, but still the quench gas is at the same height as in option 2. So if you look at the table, case 0 is when you don't have coating or quenching at all, and case 1 and 1C. 1 and 1C are the same case, but in 1C there is coating activated. In case 1, there is only quenching activating. So in case, the cases that are C are basically the cases that we have coating apart from quenching, so we have both. In cases that do not have C, except of 0, we do not have coating, but we do have quenching. And then there is a special case, which is the last one, that is 2CC, which we do have quenching, but we also have coating, and it's double the coating. So basically, we wanted to cover all these options, and with quenching, without quenching, with coating, without coating. Some of the characterizations showed us that we did indeed had a nice homogeneous coating of our nanoparticles, of our iron oxide nanoparticles. And I'm not going to go into detail right now on that, but I want to highlight here. So for the characterization of which phases of iron oxide we had, we did Mossbauer spectroscopy, which for some of you that might not be familiar with it, the results of it look like this plot that I put here. And the most important part that you have to notice is that you get this sort of double peak that shows that you have superparamagnetic activity. So based on that, we saw that we did have magnemite and magnetite phases in all of the samples, and where only those two phases, there is no other iron oxide phase on any of the samples. And I want to focus the results on the case 2, which was the option that we had the quench and coating together and closer to the nozzle. So when there is only quenching, which is case 2, the magnetite phase is 1%. But when we have coating, the magnetite phase is 20%. And when we have double the coating, the magnetite phase is even double, it's 42%, which basically tells us that coating does help us on getting more magnetite phase, and increasing the coating, it even increases even more the magnetite phase. So that was actually a very important result that we got. That was actually not that trivial. And therefore, we get the answer solution. So how does the quenching gas from the nozzle affect the produced material? So generally, we saw that the quenching of the iron oxide nanoparticles has seemed to be helped on avoiding agglomeration and aggregation, and even for an order of magnitude. How the coating gas from the nozzle affect the produced material, we saw that coating early enough and with a thicker coating increased the magnetite fraction obtained, as thicker silica coating was further reducing the diffusion of oxygen towards the core of the nanoparticles, which means that the core of nanoparticles were keeping to being less oxidized, let's say. And can different phases be conserved, and how are their magnetic properties affected? That's something that I did not really fully explain here, but basically the coating of iron oxides nanoparticles slows down the superparamagnetic relaxation, which is promising for the use of these nanoparticles in real-life applications. So with that, I would like to thank all the financial support that I've been getting through these years while doing my postdoc, as well as the co-authors, colleagues, and people that helped on the characterization techniques as well. And I will now thank you all for listening, and I will be glad to take any questions if you have any. Thank you.
Thank you, Claudia, very much for this very nice talk. I've learned a lot. For me, it's a bit out of my expertise, so it was a discovery. Thank you very much.
Mm-hmm.
I don't know if there are questions from the audience. If you have, please unmute yourself and and ask your question. So I see there is Salvatore with a question, I suppose.
Yes. Can you hear me?
Yes, thank you. Yes.
Hi, Claudia. Nice to see you. Thank you for this talk. Very, very, very interesting. I have a question regarding in the fact if there is, or if you saw a connection between the fact that you showed in some point, I think it was slide 14, that the diameter of your few layer graphene would increase as you go higher in above the nozzle, but at some point there is like a decrease. There is a sampling point when you see a decrease, and I was wondering if this can be explained also by the fact that the graphene is burned somehow, as the same as that happens when you do the sintering of your particles afterwards outside and as you've shown in one other slide. So if there is a connection, or maybe these are two different their mechanisms that occur.
Yeah, so yes, thank you for that question. I mean, it is a fair question indeed, like because it could have been happening, but that's not actually what we would expect. The temperatures are really different from the ones that we use in the oven than the ones that that the graphene is, in terms of like when it's far, like temperatures are really high at the plasma region, but of course they decay as they move farther from the plasma region. So we do not expect graphene to be burned. Actually, the expectation and what we've seen also because of the BET area would have to decrease if the graphene burns, because there is no much material. But actually, the BET area, the surface area increases. So if it increases, it means that we are not destroying material. We are still creating material. But the problem is that how is it that we create material apparently, but we have diameters that are smaller, and that's because it's more crumbled.
It's like it's collapsing on.
Yes,
on
it's
itself,
collapsing in its own. Yes, indeed, and it's also like another option that, of course, it's really hard to see, but it might be even two flakes that are close together and they start to collapse with each other. That we haven't investigated, but that could also be an option that could happen.
Okay, Alessandro, may I ask another question?
Yeah, go ahead.
Okay, yeah. The question is, how do you simulate? How would you simulate these things if you want to replicate what you saw in all these experiments?
Yeah, that's also a good question. So I will respond it in as much as I can, because I did not do that part. It's our collaborators who did it. But basically, there is not, let's say, there is not a model like a CFD model you might think or something. There is nothing like similar to that shows a flake collapsing. Not at all. Like it's much more qualitative, I would say, approach than quantitative in these terms. And it's giving a lot of suppositions. So I think the work, at least the work that we have done, or that our collaborators we've worked together with in soot and graphene in gas phase, it's still very limited, let's say. So a lot has to be done, and there is a lot of exploration to be done in that sense, yes.
So it's more like molecular dynamics kind of stuff, or framework, or
it's in between. It's not molecular dynamics, because that would be much more detailed.
Yeah. Also, the domain would be much smaller than the ones you have.
Right. So it's not to the sense of molecular dynamics, but it's not to the, considering all the fluid mechanics neither. It's kind of like in between, supposing parameters for the formation of the layers, supposing links that can be connected. So it's still a lot to explore on that way. Yes.
Okay. Thank you. Thanks a lot. Very, very interesting.
Thank you very much. Thanks. And thanks for the invitation.
I had a curiosity. So you showed that you can produce these particles, and they have different properties depending on the conditions. So what is the what is the extent to which you can control what you want to obtain? I mean, I was just wondering, what is the overall control that you have?
So yeah, that's a good question. So it depends on what you are synthesizing, but basically in the reactor itself, you do have control of the pressure that you are synthesizing at. So I did not mention it here, but for example, some of the reactions or some of the reactors, we operated at 950 millibars. Some others, in order to, for example, in the case of iron oxides, you have to go to a little bit lower pressure, because otherwise we saw that the iron oxide starts to accumulate in the top of the burner. Therefore, you have to decrease a bit of the pressure and go to 400 millibars, for example. So you can control the pressure at which everything happens. You can sort of control the temperature as well, playing with the equivalent ratios of the flame. You can control the mass flows. So you get, for example, thicker shells, thinner shells. But it's a little bit also exploration at this point. So, I mean, the concentrations, the mixtures of which is the material that you get at the end, that usually you calculate them ahead. So if you want, LATP, whatever, in a flame reactor, you can calculate how much of each material or each chemical you want, and then put them together in liquid phase and feed it to the flame, and then it's gas phase. But a lot of it also comes from trial and error as well. So it's a bit of previous knowledge, trial and error, and things that you can actually control. Yeah. And
do you also play on the let's say interaction between fluid dynamic scales and chemistry? What I mean is that you play with the residence times and
yes.
Okay.
Yes, so you also can, well, that's the idea of also the quenching. So quenching it would be one of the ways of playing with the residence time. Or making longer hot wall reactors or longer tubes, so the particles stay longer in a high temperature, for example. That will be actually the opposite of quenching. But for sure, yeah, you can definitely play with that. You can also input secondary precursors sooner or later in order to play with that too. So you do have to at least have an idea of how thermodynamically and how the fluids will move around to be able to tailor-make your material.
Thank you very much.
Yes, thank you.
I don't know if there are other questions. I don't see raised hands, so what I will do is that I thank you very much, Claudia, for this very nice talk, and we'll meet in Milan, I suppose.
Yes, we will, definitely. Definitely. Thank you very much, and thank you for the invitation. Yes, thank you.
Ciao, ciao, bye.
Bye.
Thank you. Bye.
Thank you.